Welcome back. Today we're closing out Rust's ownership story with lifetimes. Of all the features in Rust, lifetimes tend to be the one that takes the longest to click. Don't worry if they feel alien at first. Lifetimes are often the last piece of Rust to click, but once they do, the whole language snaps into focus. Lifetimes are how the compiler tracks, at compile time, how long references stay valid. You've been using lifetimes from Lesson 1. The compiler has just been inferring them for you, silently. In this lesson, we'll pull back the curtain. You'll see what lifetimes actually are, why they exist, when you need to write them out explicitly, and how the borrow checker uses them to prove that your code can never have a dangling reference. Everything in this lesson is about building intuition. The syntax is small, a single apostrophe followed by a name, but the ideas behind it deserve patience. We'll walk through why lifetimes exist, what the annotations mean, when the compiler can infer them, and when it needs your help. By the end, you'll understand the piece of Rust that more programmers struggle with than any other. Lifetimes exist to prevent one specific bug, a reference that outlives the data it points to. This is called a dangling reference or, in other languages, a dangling pointer. In languages without lifetimes, C, C++, older versions of Objective-C, you can very easily end up with a pointer into memory that's already been freed. Reading from it gives you garbage. Sometimes it crashes, sometimes it silently returns bad data, sometimes it opens up a security vulnerability that an attacker can exploit. Rust refuses to compile code that could produce such a reference. It does this by tracking, for every reference, the scope during which the underlying value is alive. If you try to use the reference outside that scope, the compiler stops you. Lifetimes are the compiler's language for reasoning about this. In the example on screen, we declare a variable r without initializing it, enter a nested scope where x is created, borrow x into r, then exit the nested scope, which drops x. After that point, r would be pointing to freed memory. Try to print r, and the compiler refuses with a clear error. The whole category of use after free bugs is off the table in safe Rust, and lifetimes are why. A lifetime is written as a single apostrophe followed by a lowercase name. Convention is to use short names, A, B, C, for simple cases, and longer descriptive names for complex ones. So, ~ticka I32 means a reference to an I32 with a lifetime named A. Annotations describe the relationship between the lifetimes of multiple references. This is the subtle part. Annotations don't change how long anything lives. They don't extend scopes. They don't do anything at runtime. They only describe to the compiler the relationships that already exist. When you write a lifetime annotation, you're saying, when this function returns a reference, it will be valid for at least as long as these inputs. Or, this struct holds a reference, and the struct must not outlive the data. You rarely need to annotate simple cases. The compiler has rules, we'll see them shortly, that cover most everyday functions automatically. But when a function accepts multiple references and returns one, you sometimes need to be explicit. When you define a struct that holds a reference, you always need to declare its lifetime. And occasionally, the compiler asks for help disambiguating subtler situations. Learning to read and write these annotations is a key skill in intermediate Rust. Here's the canonical example of where lifetimes matter in function signatures. We want to write a function called longest that takes 2 string slices and returns whichever is longer. Without lifetime annotations, Rust can't know whether the returned reference comes from the first parameter or the second. If the two inputs have different scopes, if they're valid for different stretches of time, the compiler can't tell how long the returned reference should be valid. Should it live as long as the first argument, the second, both? The annotation clears this up. We declare a lifetime parameter, a, in the angle brackets after the function name. Then, we use a on all 3 references, both inputs and the return. This tells the compiler. The function returns a reference that lives at least as long as the shorter of the 2 inputs. The caller can then use the returned value wherever both inputs are still valid. If you try to use the result after one of the inputs has gone out of scope, the compiler stops you. This is where lifetimes most commonly show up in real code, when you have a function that takes multiple references and returns one derived from them. The rule is always the same: express the relationship explicitly, and the compiler does the rest. Structs can hold references too, but because a reference is only valid for some scope, a struct holding one must also carry a lifetime parameter. The lifetime is declared on the struct, right after the struct name in angle brackets, and then each reference field borrows from it. The syntax looks a lot like generic type parameters, because lifetimes are, in a sense, just another kind of parameter. In the example, we define excerpt of tika with a single field source, a string slice with lifetime a. Any instance of excerpt lives at most as long as the string it borrows from. If you try to hold on to the excerpt after the source string is gone, the compiler catches it. Methods on lifetime parameterized structs follow the same pattern. The impl block declares the lifetime, and self takes that lifetime. This pattern, a struct that borrows into some underlying data, is common whenever you're building parsers, views, or any structure that needs to look into data it doesn't own. It lets you avoid unnecessary allocation and copying, while the compiler ensures the data stays alive as long as you need it. One special lifetime deserves its own name: tick static. A reference with the static lifetime is valid for the entire duration of the program, from start to finish. String literals, the text you write in double quotes in your source code, all have the static lifetime because they're baked into your binary and never moved or freed. You can also write types with a static bound, which says any data inside must outlive the whole program. The static lifetime is also often required by asynchronous code and multi-threaded code, because those operations can run for arbitrarily long, and anything they touch must live at least as long. Use static deliberately. If you reach for it reflexively to shut up the borrow checker, you may be papering over a real lifetime error rather than fixing it. The correct approach is usually to restructure the data flow so that ownership passes cleanly, not to declare everything static. That said, static is genuinely useful in the right places, for truly global constants, for compile time string data, and for spawned tasks that outlive their spawning context. The reason you don't constantly write lifetime annotations is that Rust applies 3 elision rules automatically. Memorize these, and most of your code will compile without any lifetime syntax at all. Rule 1. Each reference parameter gets its own distinct lifetime. If a function takes 2 references, the compiler assumes they have separate, unrelated lifetimes by default. Rule 2. If there's exactly one input lifetime, meaning exactly one reference parameter, that lifetime is copied to all output lifetimes. This covers the common case of a function that takes a reference and returns a reference derived from it. Rule 3. If a method has self as a reference, the lifetime of self is used for all output lifetimes. This makes methods that return references to self's data work without ceremony. Together, these 3 rules cover almost every function you'll ever write. When the compiler can't figure it out using them, it asks, usually with a message pointing out the ambiguity and suggesting annotations. That's your cue to add explicit lifetimes. Over time, you'll internalize these rules and stop thinking about them consciously. That's lifetimes. The deepest part of Rust's type system and the final piece of the ownership puzzle. The more you use them, the more natural they feel. And eventually, you stop thinking about them consciously because your habits naturally produce code that satisfies them. Next up, smart pointers, the types that give you controlled access to heap allocated data. See you there.